Broadcast is now starting. All attendees are in listen-only mode.
Well, good afternoon. This is Salim Khan with TEESI Engineering, and with me is Joey Pham. We'll be kind of tag teaming this presentation, and most of it is going to be covered by Joey, and I'll be just here to support him. I'll have a few slides, and Joey, do you want to go over a couple of housekeeping items that they may need to?
Yes. Hello, everyone. Good afternoon, and thank you for joining us. I just wanted to let you know that we do have the chat available to you. So if you have any questions during the presentation, feel free to post the questions or comments in the chat, and we will have some time allocated towards the end of the presentation to respond to any of your questions and comments. Also, you can raise your hand or just send us notifications if there's anything that you want us to kind of clarify.
Very good. I think we have people still joining us, so we'll just give them another 5 or 10 seconds and we'll just get started after that. Well, I'd like to thank everyone who's attending this webinar, and just keep in mind that you may have questions that may come up later on, and you're more than welcome to send an email inquiry or call us with a follow-up if you come up with questions later on. I think this presentation or webinar will also be issued in a PDF form to all that are participating, so you should be getting that in the next day or two too. Okay, I think we can get started now. Let me just do a quick overview of what we're going to be covering in the presentation. I'll just pass through the SECO technical assistance slides. There are 2-3 of them, and I'll go to them pretty fast. We will cover the solar PV payback, what's the typical measures, PV system components, just have a general discussion on those. Solar project feasibility process overview. So that's the majority of the time that we're going to spend some time is looking at the feasibility of the PV systems, and might have a case study or at least one. And then I will probably go over the construction considerations and things to watch out for, and then we'll leave like 5-10 minutes for questions and answers. So that's the general overview of the presentation. Very quickly, most of you are familiar with the SECO Local Government Technical Assistance Program. This presentation is part of that service, basically, and it is available to folks that who request it. So we can skip. It's available at no cost to mostly to public taxing entities. So it could be community colleges, county hospital, major airports, school districts. Cities and counties are all eligible for it. Very simple application, one-page document that you could send to SECO. That the application is on the right side over there, and then you can reach out to either LaShawn or myself if you've got a specific question. We can answer those. There are a lot of people in the queue that are being serviced, basically, and I expect that the new arrangement or the contract will be coming out in September, so we just watch out for that. What I wanted to do was very quickly go over some typical UCRMs, and UCRMs will stand for Utility Cost Reduction Measures, basically. So you can look at an array of UCRMs, which is TA to LED conversions, and we have given some typical payback ranges over there. Exterior lighting, motion sensors, solar, wind, window film, normally very long payback. Existing building commissioning and retro commissioning, 1 to 6 year payback. You can go down the line. HVAC systems will typically have longer paybacks, although those are the systems you all really are interested in doing. The controls will have a payback, not mentioned over here potentially specifically, but energy management control system might have a payback from 10 to 15 years also. and then boiler replacement and so forth. So the last item over there is the solar PV installation. And that has had a pretty dramatic reductions in the payback ranges from a couple of years ago. So it used to be, we barely used to be able to justify projects with a payback of 25 years or more. More and more, when we evaluate these projects and do the feasibility of these projects and look at the cost structure or the utility rate structure, the payback period has come significantly down, and it could range from anywhere to 12 to 20 tons, 12 to 20 years. And primarily the reason for that wide range is that there are each project at each location has got a very specific requirements and needs. So you have to kind of evaluate and come up cost for each location based on the specific requirements that that location might determine. So that's why you see all these ranges over here, but I just wanted to give you all a quick overview of different utility cost reduction measures and also indicating that the solar PV installations are now coming into the picture in the main fold over there also. With this, I think I'm just going to briefly go over the components over there, and then I'm going to have Joey kind of take over from me. So just a very broad overview of these things. Normally, you will have a PV modules typically on the roof. You will have a combiner box. You will have a disconnect, which is required by code on the DC side. If you have an inverter within the electrical room, you will have a DC disconnect on the left side, and then you have an AC disconnect on the right side. And from there on, when you go to your electrical panel. So just a very broad overview over there, basically. And on the right side, I think what we're going to do is cover the the PV array and the inverter a little bit more detail. So you can see on the right side also that the AC main supply, you have a meter, you have a main fuse box, this may call the switch gear basically over there. And then you have a PV generation on the other side of the meter. And then there is some sort of an interface required, and that's primarily this one line diagram is indicating. So that's just a very broad picture of a typical PV system. From here onward, I'm going to have Joey go over different PV modules that are currently out there, and then go from there onward. Thank you.
So there are many different types of solar panels. The main differences are in the cell material. This may be a monocrystalline, a polycrystalline, or thin film. And so we actually have a graphic over here showing the different efficiencies for the different types of panels. And these are just some examples. They're actually way more than this. But what you can see in general, what you'll need to know is that the polycrystalline are the lower efficiencies. Thin film is not even shown in this graphic because the thin film are much lower efficiency than that, somewhere between 10 to 15%. So the application is not really for commercial use or the roofs or larger PV systems. The monocrystalline type materials are the higher efficiency, and then there's other technologies in the manufacturing process of these solar panels that will actually increase their efficiency. And more recently, they've broken the 20% efficiency barrier, and so they're getting better and better every year. Other components of the solar panel will be the cover, the type of glass that goes over the actual material. Some of the advancements in this technology can be that they reduce the reflectivity of that surface, and that allows the cell material to capture even more of the radiant energy. Other specifications or characteristics of the solar panels that are important are the temperature coefficient of power. So this describes the change in the performance or the efficiency depending on the temperature. And usually these are rated at a standard test condition of 25 degrees Celsius or 77 degrees Fahrenheit. So when you look at the nominal wattage or efficiency of these panels, that's based on the standard condition. And the temperature coefficient of power will usually be a negative percentage per degree Celsius. So as the temperature increases, they'll lose some performance by a fraction of a percent for every degree. So in Texas, for example, typically you would see them operating at a much higher temperature than what the standard condition is. So just keep that in mind, that the performance and the efficiency of these panels actually decreases with the temperature. And conversely is also true too. So during the cold seasons, the performance may actually be improved because of this coefficient of power. So some advantages and disadvantages and drawbacks is typically the lower efficiency panel types will be cheaper. So as you look at or consider the higher efficiency or the higher performance type panels, you'll have to weigh the cost versus the performance. One thing to consider as well is that the high efficiency equipment may actually have better performance over the life of the equipment. So as you get past 15 years of service, the high efficiency units actually maintain their performance a little bit longer. So in the long run, the higher cost may end up paying itself back. So the next component of PV systems that we wanted to go over with y'all is there's different types of racking systems. So here we'll go over the ballasted types, anchored types for the fixed mount, and then there's also some tracking mount systems. So in the ballasted racking systems, these are typically static systems that they use ballast or weighted objects to secure. Usually that's on the roof, and these want to be installed on a flat or leveled roof, and these are primarily used for wind loading. Now, so some of the advantages of the ballasted racking systems are there's no roof membrane penetrations. It's a relatively simple system construction, and PV array components can be easily removed if access to the roof is required for repair. Since there's no penetrations, some of these items and components, it's not much involved to move them out of the way if any servicing needs to be done on the roof areas. So some of the drawbacks are that there's potentially structural limitations due to the additional weight of these systems compared to other types of systems, due to the nature of having additional weights to hold them down. In this graphic that we have on the top right here, you'll see that there's concrete blocks used to hold the systems down. That's primarily for wind loading requirements. And in some cases, the equipment, you may need to consult the roof warranty just to make sure that that doesn't affect the warranty on the roofs. And another thing as well is to consider whenever installing solar PV on the roof is to look at the condition of the existing roof. If it's something that y'all plan to replace soon, then that may want to be done concurrently or before the PV system is installed. And that just helps you avoid additional costs with having to move the system if it's installed before the roof work is done. So for anchored systems, this is a different type. It's the racking system that's bolted or fastened to the roof. And these are usually also for wind loading on roofs. But one of the advantages is that these can be installed on flat or sloped roofs. So if you have pitched metal roofs, then this application will work fine for that as well. So some of the advantages are they're generally lighter than the ballasted design, and they could also even be used on other applications such as carports or similar structures. So if you have some covered parking on your properties, then these could potentially be an option over there as well. Some of the drawbacks include that they may require roof membrane penetrations, and this could potentially lead to leaks down the line. Usually the contractors, when they install it, there's procedures to avoid having any leaky penetrations, but over time, some of those seals may fail. And there's a possibility of the penetrations voiding the roof warranty, but that just needs to be looked at or considered during the design phase. If you have roofing consultants, then they should be able to help with that. Or if you have the roofing contractor, if they perform the work, then it may be okay, and there may not be any issues with the warranty on that. So the third thing we wanted to go over with y'all is the tracking systems. So these, they're a little more advanced, a little more complicated, but these actually provide the most electric generation. So the way they work is they have motors and actuators actually track the movement of the sun across the sky throughout the day. And this can either be through a one-axis or a one-axis with backtracking or with a two-axis system. And that just describes the degrees of freedom in the movement of the panel throughout the day. The backtracking system is one that it has a tracking control system or a program that aims to minimize any PV panel-on-panel shading, and so you avoid some production losses with just a little bit more, maybe marginal improvement over just a simple one-axis. So some of the drawbacks with these types of systems is they're much more complex than your static PV system mounts. There's software involved, there's a lot of moving parts, there's motors and actuators, and this can lead to high upfront costs. And usually that makes the payback much higher or much longer and can be prohibitively expensive. Another drawback is that these types of systems require more maintenance. Maybe that would involve fine tuning and calibration every once in a while, and those things, some of these you may want to just install, set it, and forget it. But with the tracking type systems, if you want to maintain that maximum generation, then you'll have to make sure that the systems maintain their calibration and are functioning properly. And if there are issues with any of the systems or components, then they can be relatively expensive repair costs associated with it.
So one more thing over here is that you don't see this kind of system typically on you will actually see it in a power generation capacity, basically, right? So it's a utility scale generation. You will see these systems, although I don't expect anybody. I've not seen one anywhere where it's been installed basically for just the commercial use over there. So something to keep in mind.
So the next one of the main components of a solar system or a PV system is the inverter type. And what we want to go over today too are the two main types of inverters that are available out there. There's microinverters as well as string inverters. For the microinverters, they're generally installed 1-to-1 with the panels, but they can be 1-to-2 or 1-to-4 installed directly under the panel. So that is, you may have one microinverter for 2 panels or one microinverter for 4 panels, but typically they're 1-to-1. And the microinverters are wired or configured in parallel. The string inverters generally are a series of panels or a string and are typically located away from the PV panel arrays, and these are wired or configured in series. So to compare the two, there's some advantages and disadvantages. For a string converter or inverter, this is easy to troubleshoot. If there are issues, then you'll know right away. There may only be a few inverters in your PV system, so you don't have to look very far, or you don't have to troubleshoot too many different things. So one of the other main advantages to the string inverter is the lower cost, because you'll have fewer inverters that serve multiple strings or modules. This brings the cost of the overall system down. So one of the drawbacks with the string inverter, though, is that because they're configured in series circuits, there may be some shading effects that may only affect a small portion of the panels, but all of the panels on that string will be limited to the output of that lowest performing panel. So for example, if you have one panel that's shaded by a tree, then all the other panels connected on that string would only produce as much as the one that is partially shaded. So that's a pretty big drawback for this type of system. Another major drawback is the difficulty, or it's a little more complicated to expand on your system. So if you already have an existing PV system and you want to add to it, usually the string inverters are rated or sized based on the type of system that you have. So if you want to expand on that, you won't be able to. You'll have to change or upgrade or update your inverter equipment to match the expanded system size and capacity. One of the other main drawbacks with the string inverter is they generally have shorter lifespans compared to the microinverters. The warranties on the string inverters can be typically 8 to 12 years. So system monitoring limitations are another drawback. The string inverters will not be able to provide you with the panel level performance data. So on a microinverter, you'll be able to see the actual generation of each individual panel. But for a string inverter, you may only be able to see what the panel arrays or strings are generating, but not at the panel level. So you have a lower resolution of the performance data of your PV system. So the other drawback is the replacement cost of an inverter or a string inverter can be much higher than one microinverter. For example, if you have a microinverter fail, you just have to replace that one microinverter. But if your string inverter fails, you have to replace a much larger, more expensive unit. And I also wanted to note that there's a rapid system shutdown feature that is required by code now, but with the string inverters, that's still possible with certain combiner boxes. So now looking at the microinverter, some of the advantages are these are in a parallel circuit configuration. So this does not limit the solar panel production based on shading of other panels. So if you have one module that's shaded or has maybe a crack or a defect, the rest of the panels should operate and produce power based on their own conditions. So it's kind of independent of what's going on with the other panels. So that's a huge advantage, especially if you have the arrays configured in different areas of your building or property. And generally, these microinverter type systems will yield more electricity. This is flexible for site conditions, as I mentioned. If you have arrays on different parts of the roof, these will allow you to configure it that way, and then you don't have to worry about potential shading only for a small portion of the day, for a small portion of the system. They'll have longer lifespan, as I mentioned previously. The warranties for microinverters are typically around 25 years, so that's pretty advantageous. And there's no single point of failure. So as I mentioned earlier as well, if one of them fails, the rest of the system will actually continue to generate electricity. And you'll actually be able to see that on your monitoring system, which panel specifically or which inverter is out. And so you can address that, but the rest of the system will stay online if one goes down. So that's a huge advantage in my mind. And then also the ease of system expansion. So unlike with the string inverters, if you want to expand your system, all you have to do is add on to this one because the inverters are one-to-one with the existing system. So if you add 5 or 10 more panels, then you just need to have the inverters go with that, and then your system should continue to produce. There's not much more you have to do with that. So the drawbacks for the microinverters is the overall cost. I think it's a little bit more expensive. I think the numbers we were looking at were about $1,000 per 5 kW of the system capacity, price difference compared to the string inverters. But as the scales get larger and larger with your system, then those price differences can change. So the maintenance difficulty, for example, is one of the drawbacks because they're one-to-one. If you have an array with many panels and you find that one of them somewhere in the middle of the system is damaged, then to get to that inverter to service it, you'll have to get on the roof and then maybe disconnect and detach panels along the way, so that way you can access the specific one that's damaged. So that does add some complexity or difficulty to the maintenance compared to a string inverter, where if that one fails, it's usually in a remote location that's accessible and it's easy to get to. One of the other drawbacks with the microinverters is clipping. So clipping is when there is the panel that actually is producing more energy than what the inverter is rated for. And so you actually have some losses there where you're leaving some energy potential on the table just because the panel is producing more than what the inverter can do. And usually that's not a problem with the string inverters because they are sized for that system and they account for the additional capacity at certain conditions. So the real meat and potatoes of this presentation is going over the feasibility process or overview. So this is what we've put together is about 8 steps. And this is pretty much the process that we go through whenever we're evaluating the feasibility of a solar PV project. The first step is to select your facilities, and the second one is to identify the available space at each facility that may be able to be used for your PV system. The third one is to conduct a site visit to spot check and take some measurements of the site conditions and just observe what's going on over there and what are some of the considerations that you need to have when you're doing a preliminary evaluation of those sites. So after you collect your data from the sites, you'll need to estimate the array size, what can be done or what's possible there at each site. And then step 5, we'll use an online simulation or any software to generate potential power production. The calculations are too complicated to do by hand, so you'll want to use some software. The next step would be to account for efficiency and degradation over time, and then we can come up with project costs or estimated costs, some potential savings, and then consider any rebates that may be available to you in your area. And then the last one is to calculate the payback once the project costs and savings and potential rebates are accounted for.
So just very quickly, so this is if you're doing a preliminary feasibility is the same steps. If you're doing more detailed feasibility, it'll be the same step. But in that case, there'll be a more detailed evaluation and more cost calculations and more accurate cost estimates done. So the process still stays the same. It's just the depth of what you need to do changes from what your end goals are.
So step 1, this is the facility selection, and we just provided this graphic just to kind of show you, if you have multiple facilities that you're managing, then pick which ones you want to do, and then you can zoom in and evaluate, initially by using some satellite imagery that's available online to just see which ones potentially have some areas that you may be able to install solar.
But very importantly, you do this initially with the satellite image, but then you have to go to the field to just spot check and verify, because the satellite image may be a couple of years old and it may not reflect what you have over there.
Right. And so the second step would be to identify potential. This can be, when you're looking at the facilities you selected, it could be potentially on the roof of the building. It could be on covered parking structures if you have that on your property. There could also be in open, unshaded areas or fields adjacent to the buildings. Usually, if you do want to build it on the ground, you don't want to build it too far from the endpoint use because it'll involve additional costs with running the wires, and then there may be losses associated with that depending on how far it is. So ideally, it would be better to have it much closer to your facility. So again, at the site, you'll be taking some spot measurements and looking at the site conditions, and then we'll use the PV generation tool or modeling system or calculator to see how much energy could be potentially generated there, and that's based on the available area and then some local weather data. And usually these simulation tools or calculators will have that information kind of built in. So the third step, like we mentioned with the site measurements, some of the things that you'll be looking for are the available area. There's the tilt angle of the roof, or potential for the racking system can adjust your tilt angle to whatever you think you would use. The azimuth angle, which we'll get into a little bit in a later slide. And you'll also note obstructions from tall buildings and trees and other shading factors that might affect your PV system. So if you can note, like this picture shown here, this rooftop unit, it does shade, and the shadow will move throughout the day. So you can just kind of observe and see, how far away your system should be from the system to avoid any obstructions or shading to your PV panels or systems.
And one other thing is that that you have to stay away from the edges of the building to certain, at least 10, I would say minimum 10 feet. Otherwise, you'll have to put, railing and so forth, basically, if you're too close to the edge. So just something else to keep in mind while doing these projects.
Right. Another consideration as well is to leave some space for servicing. If you need to walk between different pieces of equipment on the roof, they'll still need access for maintenance and servicing. So that needs to be considered too. So we can't just install a solar panel over every square foot of the roof. So these are some general guidelines, or step 3 for part of step 3 of the site visit, as you'll want to measure the azimuth angle, and this will help you get a more accurate simulation or calculation of the potential energy that you can gain or produce from your solar system. And the azimuth angle is the angle or the orientation of your building or the panels in relation to true north or the sun. Ideally, what we're trying to do is to have the panels face directly to the sun to capture as much radiant energy as possible. So ideally, that would be about 180 degrees azimuth angle, which is facing directly south. And so what we've added here is this is a graph showing the annual power generation versus the azimuth angle. So as you can see, when the angle changes, between 90 degrees to 270 degrees, which is east or west, it can only be about 87 to 90% of the ideal condition. So it's you're not leaving too much on the table by having it face west instead of south. But to maximize your generation, facing south and just slightly west is ideal. This is, in my mind, because if you're having it face south but just slightly west, you'll continue to have some generation in the afternoon, which may be the peak demand period. So that can be advantageous for you as well. So you may want to consider having a slightly westward angle as well. And also, when you're looking at this graph, you'll see that the peak is actually just slightly over 180 degrees, which would be leaning to slightly west as well. So the fourth step is selecting components and system sizing. So again, if this is just a preliminary feasibility, you don't need to know exactly what all you have, but the more information you have, the better. So you can just kind of pick what you think might be good, and then that will be used in the calculator, which we'll kind of go over with you in the next steps. But you're going to want to look at what type of PV modules you want, or what kind of panels you want, like how many watts per panel, what's the weight, what's the size. So that way you can get an idea of how big you can make your system, or what your limitations are. What's the racking system types, based on your usage. If you have a really tall roof, then you'll need to consider certain types of racking system to accommodate the wind loads that you may experience. There's code requirements over there that need to be considered. What kind of inverters are you interested in, or what type of systems would work best for your application? And then there's also battery or energy storage, which is optional. Usually these systems are a little too expensive. It could be prohibitively expensive. And for the size of your facility or your needs, the batteries, it could be way too expensive to meet, for example, for a school building. The sizing considerations. So what application, are you going to be doing this for? Is that going to be on the roof? Is it going to be on the ground, or is it going to be on carports? Other considerations is you may want to do some benchmarking of your building before, or to help you decide how big should the system be. You'll want to know what's your annual kWh or electric consumption. You'll also want to know what's your peak kW profile look like, and that can help you in deciding how big your system should be. The other things, as we've mentioned, is how much area do you have, and then how much structural loading are you limited to. So we have a graphic over here showing this roof, and these are some preliminary estimates of how much area might be available for that. But usually you'll want to do less, considering some of the structural loading, as well as leaving some room to walk, and as Salim had mentioned, some offset from the edge of the roof for safety, and to be able to service different equipment on the roof as well. And then the other consideration is the dollar per watt for the installed cost. So that can help you in deciding how big should your system be, or if you should go with a certain type of technology. So the fifth step in the feasibility process is actually modeling this energy generation, or the output. And what we usually use is National Renewable Energy Laboratories, PVWatts. It's an online web app or tool, and it's completely free, and it's pretty easy to use. and we'll have some screenshots over here to show you what the user interface looks like. But this one, it estimates the electric energy generation based on the user specified design, configuration, location, and then you can also select which weather data set you want to use as well. So this one, it's pretty easy to use. There's only a handful of inputs you can put in, but it's pretty powerful as well. But let's just show you what it looks like. What's going on? Okay. So in the modeling tool, I just want to go over, these are some of the required inputs. So you have your DC system size, or how big is your system in kW. What module types do you want to use? So earlier I mentioned that there's the standard, there's premium, or there's thin film type modules. And so you can specify in the calculator, what systems or what type of components you have. What array type is it a fixed mount, or is it the open rack, or is it a roof mount? Open rack, it refers to having additional spacing for so the panels don't shade each other throughout the day. Or if you have a 1 or 2 axis tracking type system. So those can all be specified in this calculator. System losses, and these can be done at a detailed level, or you can use system defaults if you're unsure. This can account for soiling, can account for shading, line losses, degradation. There's quite a number of different things that can go into the system losses that can all be specified if you know that level of detail. So you can also specify the array tilt angle. So this is one of the required inputs, and then the array azimuth angle, as we touched on earlier. These are important inputs for the calculator. And there are also optional inputs. These at this level are, you may or may not know, and if you don't, it's okay. You can use system defaults, which are averages taken across the US. But if you do know, then you can enter this information, and that can help you get a much more accurate simulation of the potential generation at your facility at that location. So what we have over here, this table, it just shows you the nominal efficiencies of the different PV module or panel types, and then the different glass or cover types, and as well as coefficient of power. So these things that are already kind of specified in the calculator, you just use a drop-down menu and select what type you're going to use, and then all of these details or the specifications are kind of calculated already for you, so you don't have to do any of that. And some of these optional inputs, they include the AC to DC or DC to AC size ratio, the inverter efficiency, and ground coverage ratio. The ground coverage ratio is, the higher the ratio is, the narrower the spacing between the modules are. So that's what that is. But if there's any questions about any of these definitions on the calculator, you can hover over any of those aspects and it'll provide you definitions and background information for your use. So over here, we wanted to show you, this is a screenshot from the calculator itself. The first step is you'll just enter in the address of the location that you're looking at building a PV system for, and then it will take you to a satellite image, and then from there you can start entering in some more information about your PV system in question. So this slide, we're just showing you, it's a 3-step process. There's 3 main tabs in the calculator tool. Step 1 is, well, after you enter in your address, they'll have those main inputs that we touched on in the previous slide. And if you know some of these details, you can enter it in, and that can help you get a more accurate model or simulation, or you can use some of the defaults. The next step is you can actually draw or sketch your potential PV system. So since you entered your address, this is our office building over here, for example, and then you can sketch out the PV system size directly on the satellite map. You can make it as big or as small as you prefer, and then that would it'll also let you know, what's the potential kW system size based on what you sketch. And then from there, you can generate your 12 months of energy production simulation. And so that would be this third slide over here, and it shows you, how much you'll make in January through December, and then each month based on the solar radiation. And this calculator, it takes into account that typical meteorological year data. So for this area of Austin, Texas, it's using the local weather data to help it simulate some of this energy generation. So that can help you get a much more accurate picture. So degradation over time. So this is something that should be considered as well. And usually the range observed for the degradation is somewhere between 0.2 to 1% per year. And when we look at some of the solar panels, the manufacturers will provide this information in their spec sheets for different panels. And so when you're comparing what type of modules you want, you can make sure to look at this degradation ratings. On average, it may be anywhere between 0.5% to 0.8% per year. And 20% degradation is considered the end of useful life, but the systems, they will continue to produce energy even after that 20% degradation, but that's just the considered by definition when the panels are at the end of their life. So even though they're producing 80% or 20% less than what they're originally, or the nominal capacity, they'll still be able to function after that point. So step 7 in the process is considering different incentives or funding for your project. This could be some utility rebate programs. Certain utilities will have programs for solar and PV or renewables as well. Salim, did you want to jump in?
Yeah, so the SECO Lone Star program is also funding these projects, specifically if they meet the criteria. So basically something to watch out for, and they will also accept some buy down options over there if the payback is longer than what they will fund, then you can actually put some money in there and buy it down, basically where you may put 5 or 10% of the funds, and 90% of the funds you're going to get from the SECO Lone Star loan program, basically. Then these are these other qualified energy conservation bonds. There might be potential for grants and so forth coming, new clean energy bonds, and the power purchase agreements basically is where you have an agreement with somebody to provide you with the PV system to be installed on your facility, and then you buy power from them. It has got its advantages and disadvantages, and they probably needs to be evaluated on each individual case basis. But these are some of the options that are out there, basically, and I potentially am also seeing, for example, Austin ISD and few others are putting some funds in their regular bond projects, specifically for the PV systems installations and so forth. So you're seeing that trend also.
So one of the last steps in the feasibility, of course, is to calculate the cost and payback. So what we're presenting here is some typical costs of a PV system. This is just for example. And our costs are based on some 2021 published data from the National Renewable Energy Laboratory. So I think it's pretty reliable. They gather data from throughout the entire United States and they compile it. And what they found was that the price to install a solar system has actually gone down about 10% from 2020 to 2021. That's pretty dramatic, and that 10% price decrease might help make these systems and paybacks maybe more attractive or even feasible or possible. So we did some preliminary calculations based on this information from the NREL's published report, and what we found is that if you specify, for example, a 200 kW system on the rooftop, then you may have an average PV system cost something around $1,800 per kW, conservatively. And so this type of system, it may take, or it may be about 55 square foot per kW in the footprint. And the average electric generation may be somewhere around 1,300 kilowatt hours per kW of your system size. So what we calculated out is that the system may require about 11,000 square feet of space. It may cost around $360,000 and generate 260,000 kilowatt hours per year. And at a electric utility rate of 10 cents per kilowatt hour, just for example, for simplicity, this would generate about $26,000 in electricity cost savings. And using this information, the payback would be coming out to about 13.8 years. And of course, if we have more accurate data about specific location and system specifications, then we just adjust these calculations based on those site conditions. And that's how we would calculate a payback. But again, this type of example, it doesn't include any incentives or rebates or tax credits. Nope, looks like we have a question from one of our viewers. Yes, so the question from one of our attendees was, does the PVWatts website or calculator account for shading from buildings or trees? And the answer is yes. So there is, let me see if I can just kind of show y'all real quick. So this slide over here, so under the system losses, we can go into this, and then actually I think there's a drop down where you can go into even higher level of detail, and then you can calculate over here, there's a loss calculator, and it'll break it down into the different types of shading or different effects. So if you have that level of information, you could enter that in, and then that'll help account for the losses from shading from nearby structures such as tall buildings or trees on certain aspects of the system, so that can be accommodated for in this tool. Thank you for the question. So over here, this is the case study of Austin ISD. And what we're wanting to kind of show y'all or present is something, this is a study that we did back in 2019. And this one, it actually uses 2018 data. But as you can see, we have a table here aggregating some potential PV system sizes using costs at the time and the weather data at the time or from 2018. To calculate, how much potential generation could be done at these locations, as well as, how much would they generate in the first year, and then what's the average generation thereafter, as well as payback. So how much or how long will it take for this PV system at the size specified to pay itself back, as well as if it included some rebates. So we calculated it without rebates and incentives. And then the local utility over here had a rebate program. So we also did the calculation considering those potential funds as well, based on the system size and generation. And so in general, the overall scope of that, it was about $14 million in estimated cost to implement these solar systems at these buildings, as well as generating a potential almost 10 million kilowatt hours or 10 megawatts. And it's estimated to save somewhere around $600,000 per year in electric utility cost savings at an average payback of 22.4 years without incentives. And then with the incentives or rebates, it came out to about 17.7 or 17.8 years. So overall, what we've seen is that the solar payback is coming down, especially if there are some incentives that can be taken advantage of. But I think, again, this is based on 2018 data from a study conducted in 2019, and the prices of solar has gone down. And according to the National Renewable Energy Laboratories, in 2018, it was about $1.83 per watt DC for a commercial size system, anything between 10 kilowatts to 2 megawatt system. That this was a good description or average is $1.83 per watt in 2018. But for example, in 2020, the same report published said that it would be about $1.74 per watt DC. And then more recently in 2021, it's come down to $1.56 per watt DC.
However, with the supply chain issues and delays and stuff like that, it'll be interesting to see what kind of a cost impact does it have right now. And I expect or I anticipate that some of these costs may actually have risen back up or might rise back up, basically. Mm-hmm. Something to keep in mind.
Right.
Now, something about this study over there, if I recall it correctly, we also did the calculation of how much, what the savings will amount to, the amount of, vehicles off the road and how much homes you can provide power to and the CO2 emission reductions. But another interesting thing that was done over here was that we used some of these samples, and the school district had more than 120 or, they have 120 facilities. And we were able to just figure out the projection for the rest of the campuses without actually going and visiting, just to get an idea of what the total some generation capacity will be. Now, very importantly, AISD being very proactive in renewable and so forth. So they, in the bond program previously, has allocated some funds for it. In future bond programs, they may be allocating some funds. And I think they had done in their own internal analysis, and their analysis were that rather than having a PPA kind of an agreement, they want to have their own generation and so forth. The important thing over there is to keep in mind the warranty issues of the roof and the conditions and so on and so forth. Okay, so I think I'm going to be covering this part of it also. So the design and construction considerations, as I mentioned just a little while ago, one thing you got to keep in mind is that if you're planning to do a PV system on a roof, you need to make sure that the useful life of that roof is still 20 or 25 years, basically, because the PV system will be over there for a long period of time. And then if you install a PV system and that has to go through a roof, replacement or upgradation over there, major upgradation, then your roof replacement cost will be pretty significant. So something to just keep in mind. There are specific permitting and inspection requirements, and you just need to be mindful of that. Again, when you go into the design phase on these things, that's where you start addressing those issues. EU restrictions have actually come up with more specific, since the PV systems are becoming, especially the commercial one, becoming more common now, so they have more specific requirements outlined over there for them for the permitting and inspection of these facilities. So something to keep in mind when you go into the design and implementation of these projects. Of course, the structural load was discussed basically. There is a structure, you got to be aware of it. Primarily, this is not a very complicated analysis, but something you just need to be aware of it. The roof warranties, as Joey mentioned earlier, it has to be taken into account, and anything you do on the roof, you just want to make sure that whoever has the warranty is aware of it and is involved in the process, basically. Very important is the fire classification and rating. I think the new codes now require that the PV systems have the same fire rating classification that the roof system is going to have. So that's something to just keep in mind. Maintenance and monitoring is a big thing. Basically, we have been to facilities, unfortunately, where the systems are in place, but nobody knows what the generation was or if it's working or not, because for one reason or another the monitoring system wasn't working, or this is something very important, or the manufacturer who had installed it is no longer in business and they didn't know what to do or and nobody else wanted to go and fix it, basically. So something to keep in mind on these things is that this is a long-term investment. People can give you guarantees and so on and so forth for 20 years, but you need to make sure that the manufacturer and the installer is going to be there for that long. And more importantly, are you going to be there that long to maintain, to remember what the warranties and guarantees were? So they seem pretty attractive. A lot of people go for guarantees and warranties, but you need to go into more specific detail and iron those things out so that if you're not going to be there 10 years from now, that there is a system in place in which these warranties and so forth will be followed through, and that people have good understanding of those things. And more importantly, whoever is the manufacturer of these systems, installation of these systems is a reliable source for those things. Available area and module spacing, service pathways. Joey went into pretty good detail. So you want to be mindful of all these things when you're in the design phase of these things, and you need to ask questions about and make sure that those things are addressed because it will make a big difference later on when the system in operation. Keep in mind that these are systems that do need maintenance, so you need to make sure that you have access to all these modules as you go through. The roof height is kind of important. The slopes are kind of important because it has impact on the cost and an impact on the serviceability. So you need to be mindful of those things when you are thinking of these things to make sure that you're putting in a. It may look very good on a piece of paper, but you want to make sure that it's practical where you're putting it. And down the line, if you have to maintain it for 10 years down the road, there is an easy access to it, and so on and so forth. Monitoring systems and softwares are out there. They are available. They're good to have. I like to have them, on the front end or where the generation is. It's pretty impressive. You can see what is exactly happening. But we have gone through a lot of places where that system was initially installed, but people changed and so forth. Nobody remembers the password. The manufacturer is no longer there. So the system is there, but they cannot log into it. Something to just keep in mind, and if you're doing a long-term investment, 20 to 25-year investment, then those are the kind of things you want to kind of address earlier on in the specification phases and go through those details earlier on. The National Electric Code has things to say about these installations, and that's very important. So remember, this is ultimately an electrical installation. So not of NEC code applies over here. I'll just give you an example, just a general example. At one of the locations, existing locations, everyone thought it was a great opportunity to put a PV system over there. However, they went over there. When they went into the electrical room, they realized they already had 6 disconnects over there. And they couldn't install another disconnect because it would be a violation of National Electric Code. For that, they needed to upsize and consolidate all their main switch gear. When you put all of those costs into account, then it became not very feasible to do this thing. So just something to keep in mind. The rapid shutdown capabilities is required by NFPA, basically. You need to be able to shut down these facilities in case of fire and so forth. And this is something that has been developed as the popularity of these installations become more popular, those kind of codes. And then these codes will still be updated as more and more progress is made and as more of these systems are installed over there. So something we just wanted to make sure that some of these considerations are taken into account. It kind of helps in the planning phases, but it might also help in the long-term monitoring and feasibility of these systems for considerations. I think with this, we are probably ending close to our time. If we still have some questions, I think we may have a question over there or two. And we'll just read those questions and go from there. So what is it? You can read.
Okay. No, we had a question earlier from one of our attendees about the PVWatts website and accounting for the shading, which I think we answered. Hopefully that was we answered your question. Another one came in. Looks like it's just a comment. Thank you, sir, from United ISD.
Okay, so
yeah, we appreciate that.
We appreciate it. If there are we want to be respectful of your time, and if there are no further questions.
Oh, yeah.
So, there is one more
question. Another question. So, are these systems approved by SECO through the Lone Star program?
Yes, the simple answer is that, and I'll go and try to explain that. With the Lone Star program, you need to have a cumulative saving of 15 years or less. So, alone, they may not be feasible, but if you have other commissioning projects or some other low-hanging fruit lighting projects, then they could be part of the portfolio. Something to just keep in mind. Something to just keep in mind is that there are grants and block grants on its way. So I like to tell people that they should have their professionals and engineers and architects and all those kind. You need all those kind of services for some of these things. and it's good to just plan for them for energy efficiency projects. If you don't have any specific project right now, but the grant may just come from ERA grant or anything else, and if you have a team on board, which you don't need to have a contract with, basically, if there's no work, but you can actually execute some of these things much faster. So just planning for these things is half the battle. Some of these grants and all, they come pretty fast and they go pretty fast. Although my understanding is that some of the new grants that may be coming have given a little bit more time to folks to actually do these projects as compared to what it was in the past. So something to just keep in mind. With this, I think we are at the end. Again, please feel free to contact me or Joey over here if you've got any questions. And with this, I'd like to thank everyone for taking part in this thing. Hopefully this provided some information that was useful. And with this, I'd like to thank everyone and say goodbye.
All right, thank you, everyone. Also, you can be on the lookout for an email. It should be sent from our automated system, and we'll also send out the PDF slides of this presentation. And if you want to review it again, I think we'll try to put these presentations or recordings on YouTube. So you can just YouTube Texas Energy Engineering Services, and you should see our channel, and we'll have all of our webinars posted on there. All right, thank you, everyone.